All right, so today we are going to be talking about complex valued functions. Regular functions that you're familiar with, f of x equals x squared, for example, you feed in a real number x and you get out a real number f of x. It maps one set of real numbers to another set of real numbers. Complex valued functions are very similar, except you feed in a complex value z and you get out another complex value, f of z. So I could write some complex valued functions, e to the z, or alternatively I could write a value cosine of z, and both of these are valid complex valued functions. Now, how to manipulate these might not be immediately obvious, but very often with complex valued functions, we treat them in a very similar way to many other functions in physics. If we're having trouble dealing with them, we do Taylor expansions. So, if we wanted to Taylor expand this first function, e to the z, we'd have to expand it around some point. And just to keep things simple, I'm going to Taylor expand to find the Taylor series, e to the z, around z equals 0. So, to take the Taylor expansion, e to the z is going to be equal to, we evaluate this first at our point of interest, as e to the 0 is just 1. The next term, we take the derivative, and we multiply times z. We take the derivative evaluated at our point, multiplied times z, and divide by 1 factorial. So that works out to just z. We take the second derivative, still just e to the z, the derivative with respect to z, by the way. Still just getting e to the z. When we evaluate it at 0, that turns into 0, and so we multiply times z squared and divide by 2 factorial. And we could keep going with all of the terms to get this Taylor series. Now, typically when we encounter series, they need to converge in order for us to trust them to approximate our function. So, how do we check if this Taylor series converges? We employ one of our convergence tests. And so traditionally we might use something like a ratio test, where we take the limit as n goes to infinity of 2 subsequent terms, and we need to write them generally. So we take the limit of z to the n over n factorial. That is the pattern of a particular term. And we divide by the previous term. So that would be z to the n minus 1 over n minus 1 factorial. And so if we simplify this a little bit, we fix these disgusting looking fractions, we'd get, I'm not going to rewrite the limit, but just remember that it's there. We would get z to the n times n minus 1 factorial over z to the n minus 1 times n factorial. And this is going to simplify down. Z to the n over z to the n minus 1 will just give us z. And if we simplify these factorials, n factorial is n times n minus 1 times n minus 2 times n minus 3, and so on. N minus 1 factorial is the same factorial, it's just missing being multiplied by a value of n. So we end up reducing this down to z over n. And in the limit where n goes to infinity, z over infinity, when we take the absolute value of z, we're finding the length of z. It's going to be some number. And because n goes to infinity, this can get arbitrarily large, and this ratio is still going to equal 0. Or the limit of this ratio will tend towards 0 as n gets infinitely large. As long as we're worrying about a z that's less than the infinity of n, this will converge towards 0. So, what does that tell us? when we do this ratio test and we get a ratio that's less than 1, it means our series is convergent. This wasn't too hard to find for our simple function e to the z, but if we're dealing with a much more complex function, this is going to get really annoying to do. So it turns out if we use the complex plane and we look at properties of our complex valued function, we can find where the regimes of z, where our Taylor series converges, much more simply. So we're going to do that now using a different function, f of z equals 1 over 1 minus z. So our previous function converges, and it converges for basically any value of z because n gets infinitely large, but we're going to see that this function does not converge for every value of z. There are certain limits on this function. So if we Taylor expand this to figure out what we should get, we're going to Taylor expand around z equals 0. If we plug in 0, we get 1. If we take the first derivative of this and we evaluate it at 0 and multiply by z, it turns out that we just get z. And if we do this again, you can check this expansion for yourself. We end up getting 1 plus z squared plus z cubed and so on. So again, this is a function where it's very easy for us to do the ratio test, right? The limit as n goes to infinity of the absolute value of two subsequent terms, z to the n over z to the n minus 1, well, this just comes out to z. And if we're taking the limit as n goes to infinity, well, the limit's just going to disappear. We don't have an n in our absolute value sign. So what does that mean? Our ratio test says that series are convergent when the ratio is less than 1. So this ratio is only going to be convergent when the absolute value of z is less than 1. So what does this look like on our complex plane? If I draw our complex plane, real portion, imaginary portion, the absolute value of z is the length of z. And so, if the absolute value of z is less than 1, if we plot out a few points, the absolute value of z is equal to 1 when z is equal to just 1. But if z is equal to I, the absolute value of I would give us 1. We take the norm and we square root it. And so essentially, if we plot out these points around our complex plane, this circle is described by the absolute value of z is equal to 1. And so we see that this value, this series will be convergent as long as we are inside of this circle. And the circle has a special name. It is the circle of convergence. So, you could also say the radius of convergence is 1, but as long as we're using this function to describe complex values that have a norm, that have a length of less than 1, an absolute value of less than 1, this Taylor series will be a good approximation. So where does that value of 1 really come from? Well, if you look at our original function, you might notice if we plug z equals 1 into this function, we would end up getting something that is infinite. Our series blows up when z equals 1 because we have a 0 in the denominator. We can't really take derivatives at that point. So this is going to be a very important property. If we can take derivatives of our function, we can write it out as a Taylor series. We can do calculus on the series, we can manipulate these terms, and we can trust that our result will be convergent. So we will use this result in order to expand many different complex valued functions and know where we are allowed to manipulate them, where we can trust the series, and how to deal with them when we're using them in integrals.